Hello students, welcome to the EPG Pathshala. I am Ashok Goel from the Department of Physics and Astrophysics, University of Delhi. Today we will continue to discuss about the use of group theory in quantum mechanics from the paper Mathematical Physics. So let us see what we are going to learn in this module. In this module, we will learn about the connection between the symmetry of the Hamiltonian and the atomic levels. We will see that from purely group theoretical considerations, we can learn a lot about atomic spectra. We can learn about selection rules for atomic transitions. Let's first discuss the electric and magnetic dipole transitions selection rules. Remember that the electric dipole moment is mu is equal to epsilon r and is a polar vector which changes sign under reflection with the components along the x, y and z directions. On the other hand, the magnetic dipole moment is an axial vector operator which does not change sign under reflection, and we'll consider the electric dipole moment as well as the magnetic dipole moment as the perturbations through the operator V. The dipole operator V transforms according to the appropriate irreducible representation gamma V. The irreducible representation of the symmetry group of the perturbed Hamiltonian. To find the transition between two states belonging to irreducible representation gamma 1 and gamma 2, say, we need to know the direct product of the gamma V and gamma 1. So, we are considering a transition from gamma 1 to gamma 2 in the presence of a perturbation, and perturbation operator transforms as a reducible representation gamma V. So, what we do, we take the direct product of gamma V with gamma 1 and resolve it into the irreducible representation of the original symmetry group. Then the transition from the state belonging to irreducible representations gamma 1 to gamma 2 will be allowed if and only if the direct product of gamma V with gamma 1 contains the irreducible representation gamma 2. Otherwise, there will be no transition. We will illustrate this with the help of some examples. I will now illustrate this with the help of an example. Now consider the symmetry of the unperturbed Hamiltonian to be the symmetry CV. It can be seen from the representation table of CV that the Z component of the dipole operator, which transforms as the component Z of a vector R, it belongs to the representation A1, whereas the X and Y components belong to the representation E. Thus, the operator or the dipole operator V is, or its representation gamma V is A1 plus E. And now from what we have learned, unless the direct product of the irreducible representation of C3, which we take gamma 1, with gamma V, which transforms as A1 plus E, contains the irreducible representation gamma 2 of C3, the transition gamma 1 to gamma 2 is not allowed. So, transition to allow, gamma 2 must be contained in the representation. Let us look now at the character table. As I explained, the Z component transforms as A1 and X and Y components as E1. We now construct the direct product of the irreducible representations. So for example, A1 cross A1 is given in the table as shown, and when we resolve it in terms of the irreducible representation of C3, we find that A1 cross A1 is equal to A1, where A1 cross A2 is equal to A2. A1 cross E is E, and likewise E cross A2 is E. E cross E is A1 plus A2 plus E. A2 cross A2 is A1, and A2 cross A2 is E. So what do we learn from this? So what we learn from this is that since the electric dipole operator has components x, y, z, which belong to the representation A1 and E, therefore the electric dipole operator belongs to the representation A1 plus E. It is now clear that A1 cross A1 plus E does not contain A1, therefore the does not contain A2, therefore the transition A1 going to A2 is forbidden. From E cross A1 plus E, which is equal to E plus A1 plus A2 plus E, we see that the transition from E to A1, E to A2, as well as from E to itself are all allowed. Likewise, A2 cross A1 plus E is equal to A2 plus E. Therefore, A2 going to A2 and A2 going to E is allowed, but A2 going to A1 is not allowed because A2 cross A1 plus E does not contain A1. We consider the magnetic dipole transition from a state gamma 1 to gamma 2. Remember that the magnetic dipole moment is an axial vector whose z component transforms like the irreducible representation A2, whereas its x and y components transform according to the irreducible representation E. So the magnetic dipole transition from gamma 1 to gamma 2 will be forbidden if neither the direct product of A2 with the representation gamma 1 or the direct product of E with the representation gamma 1 contain gamma 2. Now we see from the table that the direct product of A1 with A2 plus E, remember A2 stands for the irreducible representation of the Z component of the magnetic moment and E for the X and Y component. So that the direct product of A1 with A2 plus E can be seen from the table and can be resolved from the character table that this product is the sum of A2 plus E, which does not contain A1, and likewise the direct product of A2 with A2 plus E is equal to A1 plus E and does not contain A2. Whereas the direct product of E with A2 plus E contains E plus A1 plus A2 plus E. It is clear that the transition A1 to A1 and the transition from the state belonging to the irreducible representation A2 to A2 are completely forbidden by the magnetic dipole operator from group theory considerations. Let me give another example. Now consider the electric and magnetic dipole transitions for a system which has a cubic symmetry O. Earlier we considered the symmetry C3V. O has the following character table which are shown on your monitor. The x, y, z components of the dipole operator transform according to the irreducible representation of the group O. Namely, the xyz components transform as the representation T1, whose characters are given in the table as 3, 1, -1, -1, and 0. So T1 is the the dipole moment transforms like T1. So we take the direct product of T1 with the irreducible representations of the group O. So we have shown here T1 cross A1, for example, has the characters 3, 1, -1, -1, 0, which can be resolved, and T1 cross A1 is equal to T1, whereas T1 cross A2 is equal to T2, T1 cross E is equal to T1 plus T2, and T1 cross T1 is equal to T1 plus T2 plus E plus A1 and T1 plus T2, which has the characters 9, -1, 1, -1, and 0, can be resolved into the irreducible representations of the group O as T1 plus T2 plus E plus A2. So from this it's clear that the transitions from A1 to A1, A2 to A1, E1 to E, A1 to E, E2 to E, T1 to A2, and T2 to A1 are all forbidden. So you can see how powerful this method is to give you the selection rules. Now let us consider another example. In this example, we will consider a system with the symmetry D to D, and we'll try to find out the selection rules for electric dipole radiation. The character table of D to D is given. The Z component of the vector belong to the irreducible representation A2, whereas the X and Y components belong to the irreducible representation E. So what we have to do then? What we have to do is to find which representation are contained in the product of the representations B2 and E with all the representations of D to D. So we can construct a table with the product of the representations and resolve them into the irreducible representations of the group D to D. So when we do that, we have A2 cross A1 equal to A2, A2 cross A2 equals A1, A2 cross B1 is equal to B2, A2 cross B2 is B1, A2 cross E is equal to E, E cross A1 is E, E cross A2 is E, E cross B1 is E, E cross B2 is E, where E cross E is equal to A1 plus A2 plus B1. So what does it tell us? It tells us that for the Z component of the electric dipole radiation, Z component transforms as A2. The allowed transitions are then A1 to A2, B1 to B2, E to E, while for the XY components, the only allowed transitions are from A1 to A2, B1, B2 to E. I'll now discuss the atomic symmetries of the atom. Now remember that in a single particle model of the atom, the electron is assumed to move on an average in the central potential of the nucleus and the rest of the electrons. The potential, and therefore the total Hamiltonian, is an invariant under three-dimensional rotation group because we assume the electron to be moving in a central potential. We saw earlier that the three-dimensional rotation group O3 is the direct product of the special group SO3 and the inversion group O, inversion group with elements E and I. That is, the group O3, the group of three-dimensional rotations, can be written as a direct product of the group SO3 and the inversion group, which have the elements E and I, where I is the inversion operator and E is, of course, the identity. The two one-dimensional irreducible representations of the inversion group are represented by sigma plus and sigma 1. This has two elements and two classes. It has only two irreducible representations. Both are of dimension 1, which we have represented by gamma plus and gamma minus, such that gamma plus, the character of gamma plus for E and gamma plus for the symmetry operation I is +1, where gamma minus for the identity operation is +1 and gamma minus for the inversion operator is -1. So gamma plus is the identity representation of the group. The irreducible representation of the O3 are thus the direct product of the irreducible representation SO3 and those of the inversion group, namely the representation themselves, DL sigma being the representation of the group O3, is equal to the direct product of the representation dl of the group SO3 with the representation gamma sigma of the, which is the irreducible representation of the inversion group, where we have represented the irreducible representation of the group O3 by DL. By DL, sigma takes two values, plus or minus, and DL represents the usual irreducible representation of the group SO3. So DL is the irreducible representation of the group SO3. DL sigma is the irreducible representation of the group O3. The elements of the group O3 can be divided into two categories, say chi and I chi, where chi stands for the group elements of SO3. The matrices of DL sigma are then given by DL sigma is obtained as a direct product of DL and gamma V. DL for the symmetry element X and D gamma for identity, which itself is equal to DL X, and likewise DL sigma IX is equal to DL X into sigma gamma sigma I, so that DL plus IX is equal to DL and DL minus IX is equal to minus DX for all X belonging to the group SO3. The eigenfunctions of an electron in an atom thus belong to any of the irreducible representation DL sigmas. If an eigenfunction belongs to DL plus, then it is invariant under inversion and is said to have even parity. Eigenfunctions belonging to DL minus change sign under inversion and are said to be of odd parity. The parity of the wave function depends only on the spatial part of the wave function, the spin part being invariant under the inversion x, going to minus x. Now, in a one electron atom, all the irreducible representation DL sigma are not allowed. If L's are the orbital angular momentum of the electron, its wave function under coordinate inversion is multiplied by minus 1 to the power L. I guess you are already familiar with this, that if L is the orbital momentum of the electron, then the wave function under coordinate transformation is multiplied by minus 1 to the power L. And therefore, only irreducible representation which are allowed in one electron atoms are D0 plus, D1 minus, D2 plus, and D3 minus, etc., corresponding to L is equal to 0, 1, 2, 3. In multi-electron atom, the parity of the combined wave function of the electron is minus 1 to the power L, where L is the sum over all the Li's, where Li is the orbital angular momentum quantum number of the ith electron. So, which means that the only irreducible representation of one electron system in the S shell has even parity, in the P shell has negative parity, in the D shell has positive parity, and so on. Now let me give an example to illustrate what I have said before. Let's consider a two-electron atom which has both the electrons in the P shell, that means L is equal to 1. The wave function of each electron transform according to D1 minus, because an electron is in the P shell, so its parity is negative. So the wave function of each electron transform according to D1 minus. The product wave function will therefore transform according to the direct product representation, D1 minus into D1 minus. And remember that when you add the angular momenta 1 plus 1, then you have the answer 2, 1 and 0. So D1 minus into D1 minus is D0 plus D1 plus D2 plus. The direct product into three representations, all of the same parity which is positive because both the electrons are in the negative parity and that product has positive parity, and therefore the direct product of the two electrons in the p shell has a representation as a sum of representations corresponding to L is equal to 0, 1 and 2, all with the even parity plus. Thus the atom can be in this state L is equal to 0, 1 or 2 with even parity in each state. So let me illustrate it for the case of many electron system. Now transition under electric dipole operator from a state dl sigma to dl prime sigma will be allowed provided the direct product representation d1 minus with dl sigma contains dl sigma prime, dl prime sigma prime. You can remember that the dipole operator transforms a d1 minus, so we'll have to take the direct product, so d1 minus with dl sigma. Now d1 minus, which is how the dipole operator transforms, the representation is d1 minus, so direct product of d1 minus with dl sigma is equal to dl minus 1 sigma plus dl minus sigma plus dl plus 1 minus sigma, provided L is not equal to 0. If L is equal to 0, then d1 minus into d0 sigma is simply d1 minus sigma for L is equal to 0. So thus the transition between two states with L is equal to 0 is forbidden. Secondly, the transition from dl sigma to dl plus minus sigma is allowed. There is a transition in which the angular momentum changes by a unit amount and the parity is reversed. Only those transition between those states only are allowed. Therefore, delta L is equal to 0, plus minus 1 are allowed, provided the final state have opposite parity. I'll now discuss the Zeeman effect, with which you are all familiar from your undergraduate studies. Let us consider an atom in the state specified by the quantum numbers J, M and N. We know that this state has 2J plus 1 fold degeneracy corresponding to the values of M lying between minus J to J in steps of 1, and the energy eigenvalue E and J does not depend on the quantum number M. So there is a 2J plus 1 fold degeneracy in the energy levels. Now if the atom is placed in a uniform magnetic field B, the degeneracy of the level is completely lifted and the level E and J splits into 2J plus 1 non-degenerate levels. We can easily understand this result from group theoretical considerations. Remember that the symmetry group of the atom is SO3 if J is an integer, and the symmetry group is SU2 if J is half an odd integer. Consider first the group to be SO3. Then the state JMN contains spherical harmonics YLN theta phi, whereas if the group is SU2, the state transforms as FJM, which we had defined earlier. Now if the atom is subjected to perturbation provided by a uniform and constant magnetic field, which for simplicity we take along the z-axis, then the total Hamiltonian of the atom is H equal to H naught plus mu dot B, which is equal to H naught plus mu B into G J dot B, and if B is in the z direction, then this can be written as H naught plus mu B G times B into Jz. Remember here, mu B is the Bohr magneton and G is the gyromagnetic ratio. The total Hamiltonian is now invariant only under rotation about the z-axis. So the symmetry of the Hamiltonian has been reduced in the presence of the magnetic field from the full symmetry to the, or rotation to the symmetry only along the z direction, z axis. The symmetry group of the system is thus reduced to SO2, which is the subgroup of SO3, or the SO3 is reduced to SO2. Now SO2 is an abelian group and has only one-dimensional representations. Thus we can see from the above discussion that the unperturbed state represented by the quantum numbers j, m and n cannot remain degenerate for all values of L lying between minus j to j. The eigenfunction jmn now belong to the irreducible representation of SO2, and therefore the 2j plus 1 fold degeneracy is completely lifted by the magnetic field. The eigenfunction jmn being also the eigenfunction of the z component of the angular momentum, namely j sub z, the energy of the total Hamiltonian is now given by the energy of the unperturbed Hamiltonian plus the energy of the magnetic energy, and therefore the total energy E with subscripts njm is equal to Enj being the energy of the unperturbed Hamiltonian plus mu b g times b into m, because the z component of the angular momentum has the eigenvalue m and the perturbation is mu dot b. If b is in the magnetic field is in the z direction, then it is the z component of the angular momentum which contributes, which has the eigenvalue m, and thus the total energy E njm in the presence of the magnetic field, which is assumed here to be along the direction z, is equal to Enj plus mu b times gbm, where g is the gyromagnetic ratio. Thus the magnetic field splits an atomic line corresponding to a total angular momentum value j into 2j plus 1 equally spaced lines. This is called the Zeeman effect. So, students, let us summarize what we have learned in this module. We have learned that the transition from the states belonging to the irreducible representations gamma 1 to gamma 2 will be allowed if and only if the direct product of the irreducible representation of the perturbation, namely gamma v, with gamma 1 contains gamma 2, otherwise not. The magnetic field splits an atomic line corresponding to a total angular momentum value j into 2j plus 1 equally spaced line, and this is the Zeeman effect which you already know. Thank you.